I'm Dr. Jim Zoval. You're about to watch one of my video lectures. If you like this video and would like to get videos for your entire General Organic and Biochemistry course, you can do so at www.zovallearning.com. I'll give you more information about that at the end of this video. I'm going to start this video with a definition. Let's define molecular geometry as the spatial arrangement of a molecule's atoms. By spatial arrangement, I mean how the atoms are arranged in 3 dimensions. These videos are made to be viewed while using fill-in lecture notes. The pause in the audio is to give students time to complete the lecture notes fill-in. The lecture notes can be downloaded, free of charge, at www.zovallearning.com. Molecules very rarely take the shapes that are drawn in their structural formulas. Structural formulas, whether line bond, condensed, or skeletal, are either 1- or 2-dimensional. For example, we drew the line bond structure of a water molecule, H2O, in 1 dimension. All atoms were along the same line. The line bond structure shows us the atomic connectivity and the location of lone pairs. The line bond structure does not show the actual molecular geometry of the water molecule. You'll learn later that in a water molecule, all of the atoms are not on the same line. Consider this line bond structure of sulfur trioxide. The line bond structure shows us the correct atomic connectivity, a sulfur bound to 3 oxygens. It also explicitly shows the location of lone pairs in the molecule. The line bond structure depicts the atoms in 2 dimensions, all on the same plane. However, the molecular geometry of sulfur trioxide is 3-dimensional. All the atoms are not on the same plane. Like sulfur trioxide, most molecules are 3-dimensional. Line bond structures are commonly drawn with the lines, the bonds, at 90-degree angles, but the bond angles in molecules, that's the angle between covalent bonds, with rare exceptions, are not at 90 degrees. Skeletal and condensed structures often use bond angles of 90 degrees or approximately 120 degrees only for convenience in depicting the bonding pattern connectivity, not necessarily to represent the actual bond angles or geometry of the molecule. I want to clarify this using an example. Fentanyl is a therapeutic drug used for pain relief and is combined with other compounds to be administered as an anesthetic. It's about 100 times more potent than morphine. The skeletal structure of fentanyl is shown in this view graph. The geometry of the molecule can be depicted in 2 types of views. A ball and stick model, which is shown on the bottom left of this view graph. Ball and stick models are images that are intended to show molecular geometry using perspective graphics. The other type of view that shows the molecular geometry is called a space-filling model. Space-filling models, like ball and stick models, are intended to show molecular geometry, but also depict the scaled size of the atoms. In both the ball and stick model and the space-filling model here, carbon atoms are shaded black, oxygen atoms are shaded red, nitrogen atoms are shaded blue, and hydrogen atoms are shaded white. Images of ball and stick or space-filling molecules are best viewed when they can be rotated in 3 dimensions, as shown on the bottom right for the space-filling model of fentanyl. I used the term bond angle earlier. Let's take a moment to get it in your notes as a definition. A bond angle is the angle between 2 covalent bonds. I told you earlier that structural formulas, whether line bond, condensed, or skeletal, do not explicitly show the actual bond angles within molecules. However, and this is the main educational goal of this video, the actual bond angles can be predicted from a molecule's structural formula. Let me draw your attention back to the ball and stick model of fentanyl. Remember, molecular geometry was defined as the spatial arrangement of a molecule's atoms, how the molecule's atoms are arranged in 3 dimensions. To know the exact molecular geometry, we must know all of the bond angles. and bond lengths. A bond length is the distance between two bonded atoms within a molecule. One example of a bond length between two carbon atoms is called out in this view graph. In this course, we'll ignore variations in bond lengths within molecules since these relatively minor deviations in length don't significantly affect the concepts that we'll be discussing. Therefore, for our purposes, predicting molecular geometry will be equivalent to predicting the bond angles within a molecule. As I discuss the geometry of molecules, I'll often categorize molecules by their size. The three size categories that we'll use in this course are defined as follows. Diatomic molecules. A diatomic molecule is a molecule that contains only two atoms. The atoms in a diatomic molecule could be the same element, for example H2, or the atoms can be different atoms, for example HCl. The main point being that a diatomic molecule contains only two atoms. The next molecular size category is the small molecule category. A small molecule has one central atom with all other atoms bonded to the central atom. Examples are CH4 and H2O. The third molecular size category is called the large molecule category. These are larger than the small molecules. There's not just one single central atom with all the other atoms bonded to it. An example of a large molecule is propane, C3H8. Note that in propane there's not just one single central atom with all the other atoms bonded to it. Now that you know our molecular size categories, let's return our attention to the geometry of molecules. For diatomic molecules, the geometry of the molecule is always linear. The two atoms that make up the molecule exist on the same line. For small and large molecules, bond angles can be predicted from the structural formula using a model called valence shell electron pair repulsion theory. The central idea of valence shell electron pair repulsion theory is that bond angles around any particular atom of interest in a molecule can be predicted because these groups of electrons surrounding this atom will repel each other. These electron groups, sometimes abbreviated as EG, consist of, as the name implies, groups of electrons that are localized to a certain area. Since electron groups are composed of electrons which have a negative charge, the electron groups repel each other as shown in this illustration because of electrostatic repulsion. You can easily recognize an electron group by looking for one of the following: a bonded atom, that's an atom that's bonded to the atom of interest. Each bonded atom counts as one electron group. Whether the bonded atom is connected to the atom of interest with a single, double, or triple bond, all of these shared electrons are localized within a particular region and therefore count as one electron group. The other thing that makes up an electron group is a lone pair on the atom of interest. Each lone pair counts as one electron group. Even though lone pairs are not attached to other atoms, they do occupy a localized area around the atom of interest and therefore repel other electron groups. The key to valence shell electron pair repulsion theory is just these groups of electrons, whether they're the bonds to an atom or whether they're lone pairs, repel each other. Let's start off with something we're familiar with. Let's start off with, instead of electron groups, instead of bonded atoms and lone pairs, you guys, have you ever taken blown up a balloon and rubbed it against a fabric or a natural fur and it develops an electrical charge, right? And then if you do that to two of them, you try to put it together and the balloons move apart from each other, right? Or that attracts something that has a positive charge, like maybe you hold it in your hair and your hair moves towards the balloon. So if we take a couple balloons and we're going to put these couple balloons in a clear
let's say this is a clear plastic hollow sphere. So it's a big sphere, it's clear, it's hollow inside. We could put these things in it. And we take a couple balloons, and we won't turn the charge on yet, but as if we could magically then give them static electricity, give them the same charge, like a negative charge, what would happen there?
Try to imagine what will happen to these two balloons if they both have a negative charge.
All right, let's see if you're right. Let's turn on the charge. Is that what you pictured? Yeah, electrostatic repulsion, right? Valence shell electron pair repulsion theory. Is this really, really hard? Sounds hard, but it's not, right? Electrostatic repulsion causes those balloons to move as far apart from each other as possible. The same thing happens with electron groups. I wanted to keep it something you're familiar with. Now we'll go to something that's a bit more abstract, these electron groups. Let's see how well your memory is doing. There are two things that make an electron group. What are they? What? A bonded atom, that's one, and a lone pair. So now we're going to do this with electron groups. Draw the line bond structure for CO2. Let's do this together. A lot of you guys got it. I'm going to go through the steps here. Step one, on our sixth step for drawing line bond structure, we got to figure out how many total electrons we have. There's one carbon. So we have 1 times 4 electrons from carbon, so a total of 4 from carbon. We have 2 oxygens, so there's 2 times 6 electrons from oxygen, so we have 12 from oxygen. We should have a total of 16 electrons in the structure. So far, okay? Right? Step 2, we're going to connect these atoms together with single bonds in the most symmetric way possible. When we're doing symmetry, when we're looking at these small molecules, you see how there's one of one atom and more than one of the other? There's one carbon and more than one oxygen. The atom that there's just one of, that's the one that goes in the middle. That's the central atom. We bond all the other atoms to that central atom for small molecules like this. So I'll put the carbon here, and I'll bond the oxygens to the central atom. That's what we call the skeleton, the bare bone. How many electrons did I use there? 4. Step 3 tells us how many more electrons we have to add. So in step 3, I'm going to subtract the number I used from the total. So I know I'm going to have 16. I used 4 in the skeleton. It tells me I have 12 more electrons to add. Step 4 tells me how to add them. I add them as lone pairs, not individual dots, not bonds, lone pairs, as evenly as possible. Their electrons are negative. They repel each other, so you spread them out. That's what nature does. So there's 2, right? There's a lone pair. 4, 6, 8, 10, and 12. That's what I do in step 4. So far, all right? Questions so far? We go to step 5, we check for octets. We check every atom in the molecule. Is carbon surrounded by 8 electrons? Yeah. Is oxygen? No. And this oxygen? No, right? So we have to go to step 6. If the octet rule is not satisfied, we're going to change lone pairs into bonds. We're going to make either double or triple bonds. So let's think about this. We got a lot of choices here. Which one should I change? Now, this oxygen has 6 electrons. It needs more electrons. So if I move these two over here, does that help? So you might do that. You might say, no, that didn't help. Put them back. Put them back. Would it help if I move these two over here? So let's do so. Now, every time I do that, I go back and check for octets. Don't move other things around until you check for octets. Octet satisfied? Here? 2, 4, 6, 8. Yeah. Here? No. So I have to work on this. So now I'm going to go back to step 6. Change lone pairs into double or triple bonds. Which are we going to move these on the carbon or the ones on the oxygen? Carbon, right? So I'll put those there. Notice I'm not just adding it. I'm changing lone pairs into double or triple bonds. Every time I do that, I check for octets again. Is the octet rule satisfied for every atom in that molecule? What do we do when that's true? Right? Stop. Don't keep adding electrons or making more bonds. There we go. So let's now construct this like we did the balloon. The central atom will be in the middle. And we're going to arrange those electron groups as far apart from each other as we can. How many electron groups are on the central atom? Let's see. What makes an electron group? Two things: a bonded atom, a lone pair. So is anyone who said 4 wish to change your answer to 2, right? One bonded atom, another bonded atom. These electrons, they're 4 electrons, but they're all kind of grouped together between these 2 atoms. It's 1 electron group. Don't call triple bonds 3 electron groups or double bonds 2. It's just a bonded atom there. So 2 electron groups. Each bonded atom counts as 1 electron group. So just like we did the balloons with the charge, we're going to place these electron groups as far from one another as possible. So there they go, far from each other as possible. Just like the balloons. Make sense? Is valence shell electron pair repulsion theory really, really hard like it sounds? It's quite simple, right? So let's do 3 electron groups. Let's think about this with the balloons first. We'll put the balloons in the sphere, and then we'll magically turn on the charge, and we'll see what happens. Right? They spread away from each other as far as possible. It turns out what geometry is that they're all on the same plane. Any plane you could draw this on, any plane that goes through the origin of this sphere, you could draw it there, but they're all 3 there. They make kind of like a triangle if you're looking straight down at those. Triangle all on the same plane. Let's look at the same thing now with a molecule. Draw the line bond structure for sulfur trioxide, SO3.
Click pause and work on the line bond structure.
So here we have the line bond structure for sulfur trioxide. Let's put the sulfur in the middle of the sphere. How many electron groups are on the central atom? 3 electron groups on the central atom. Each bonded atom counts as 1 electron group. Let's put them in there. Just like the balloons. With 3 electron groups, all atoms are on the same plane, and we have 120-degree angles. If we rotate that sphere to kind of look down the top, it would look like this. Right? You're looking straight. Now the atoms are on the plane of the screen, all these angles, this angle, this angle, this angle, 120 degrees. That's just the geometry of putting the electron groups as far apart from one another as possible. Line bond structures, they don't explicitly tell us the bond angles. In other words, we can't look at that. We draw usually all 90-degree bond angles in line bond structures. It doesn't explicitly tell us the bond angles. What we're doing right now is, given this, figuring out how these atoms are arranged in space. The line bond structure just shows the connectivity. We have to use a little bit of reason to get the bond angles. Let's do an example that has 4 electron groups. So let's think about the spheres first. We'll put them in there and then turn the charge on and see what happens. They spread apart, right? Because they're all negatively charged. Far apart from each other as possible. Valence shell electron pair repulsion theory. Let's do this with electron groups now. We're going to draw the line bond structure of methane. So why don't you, if you're watching the video, click pause and draw the line bond structure of methane. Let's do this together. CH4. We see the formula. There's 1 carbon and there's 4 hydrogens. So when we see just one of one atom and more than one of another on a small molecule, we know the atom there's just one of, that's going to be the central atom. Let's step one. How many total electrons? One carbon. So 1 times 4 electrons. We have 4 electrons from carbon. There are 4 hydrogens. So 4, each hydrogen has 1 electron. So we get 4 electrons from hydrogen. So we have a total of 8 electrons we're going to see in the line bond structure. We're going to draw the skeleton. Bare minimum, hook them together with single bonds. One central atom, all the other atoms connected to it. That's step 2. Step 3, figure out how many more electrons we need to add. We knew we were going to have a total of 8. How many did I use in the skeleton? 8. Uh-oh. No more to add. I hope the octet rule is satisfied. Is it? Oh, good. Then we're done. Methane. We'll put the carbon in the middle. How many electron groups are around the central atom? 4. Put them as far apart as possible. Valence shell, electron pair, repulsion theory. And it has this geometry. When you have this geometry, you get this 4-sided arrangement. It's like a pyramid with a triangular base. So 4 sides, the base, and the 3 sides. Electron groups are arranged at about 110-degree bond angles. We'll round them off to 110. That's just nature. That's just geometry. How do you put 4 objects as far apart from one another as possible? What are the bond angles? They came out to be about 110 degrees. When you have 2 electron groups, what are the bond angles? 180. When you have 3 electron groups, what are the bond angles?
120.
All on the same plane, right? If you bring one of those off that plane, it gets closer to the other one. So they're all on the same plane at 120 degrees. When we get to 4 electron groups, that's when we need to use 3 dimensions. 4 electron groups. What are the bond angles for 4 electron groups?
110.
110.
A quick disclaimer here. For atoms surrounded by 3 or 4 electron groups, the angles will deviate slightly from 120 degrees and 110 degrees when one or more of the electron groups is a lone pair. The reason for this is that lone pairs exhibit slightly more electrostatic repulsion than do bonded atoms, and therefore push a little bit more strongly on the other electron groups. In this course, these slight deviations in bond angles caused by lone pairs can be ignored because their effects are not significant in the chemistry that will be discussed. You can get your entire general, organic, and biochemistry course as a series of video lectures. The rental period is for 1 year, so you'll have these video lectures for the entire term of the course. You could watch the videos whenever and however many times you wish. I survey my students and they prefer these video lectures over the textbook by a ratio of about 10 to 1. Fill-in lecture notes and an electronic version of my textbook are available free of charge at the website. To get more information or to get the videos, free textbook, and free lecture notes, visit my website at www.zovallearning.com.